We have seen that with every random variable we may associate a function, namely the cumulative distribution function, or CDF. We will now introduce two other functions that can be associated with certain random variables, namely the probability mass function and the probability density function. Typically, we will classify random variables into one of two types. A random variable x is said to be discrete if it only takes a discrete set of possible values, enumerated here as x1, x2, x3, etc. In that case, we define its probability mass function at a point x to be the probability that capital X is equal to that value little x. In that case, the probability mass function evaluated at each of these possible values xk must be greater or equal to 0 because it is a probability, and the sum of all of these probabilities must be equal to 1. On the other hand, a random variable capital X is said to be continuous if it has a probability density function which satisfies the following equation. The probability that capital X lies between a and b is the integral from a to b of the density function. In that case, again, we have that the density function is non-negative. And the analogous result to this statement over here, that the sum of the mass function is equal to 1, is that the integral of the density function is equal to 1, where we integrate over all possible values of x. If a random variable is continuous, in other words, if it has a density function, then the probability that x is equal to a would be equal to the integral from a to a of f of x, and that would be 0 for all a. In other words, for a continuous random variable, the probability that it takes a particular value is always equal to 0. For a discrete random variable, this need not be so. Note that the values of a probability mass function must always be between 0 and 1. However, the values of a density function may be greater than 1. All that is required is that the integral adds up to 1. The CDF, capital F sub x, and the density or mass function, little f sub x, of a random variable capital X are closely related. First, consider the case where capital X is a discrete random variable taking values x1, x2, x3, etc. In that case, by definition, capital F evaluated at little x is the probability that capital X is less than or equal to little x. And since the values of capital X are x1, x2, x3, etc., this is the probability that capital X is equal to xn for some n so that xn is less than or equal to x. By additivity property of probabilities, this is just the sum over all n where xn is less than or equal to x of the probability that x is equal to little xn. And that is just the sum over all n where xn is less than or equal to x of the probability mass function. Hence, the cumulative distribution function evaluated at point x is just the sum of the probability mass function over all values xn where xn is less than or equal to x. On the other hand, if we look at the probability mass function evaluated at xn, by definition this is just the probability that capital X is equal to xn, and that is the same as the probability that x is less than or equal to xn, but x is not strictly less than xn. If capital X is less than or equal to xn but not strictly less than xn, it must be equal to xn. And this, by definition of CDF, is just the CDF evaluated at xn minus the value of the CDF just before we hit xn. In other words, it's the size of the jump in the cumulative distribution function at the point xn. On the other hand, if x is a continuous random variable, then by definition, f evaluated at little x is the probability that capital X is less than or equal to x. In other words, the probability that capital X lies between minus infinity and x, and therefore it is the integral from minus infinity to x of the density function. If we now apply the fundamental theorem of calculus and we differentiate the CDF, we get the PDF. And so the density function is the derivative of the distribution function. Alternatively, the distribution function is the integral of the density function. Let's give an example. A random variable x is said to have the binomial NP distribution if the probability that capital X is equal to little k is n combinatorial k times p to the k times 1 minus p to the n minus k. We'll have more to say about this distribution later on, but here is some intuition. In a sequence of independent random trials, each with two outcomes, which we call success and failure, the binomial distribution gives the probabilities of the number of successes in n trials if the probability of success is p. As an example, if a coin has a probability p of landing heads, which we call success, and if x is the number of heads in n trials, then x will have a distribution which is binomial NP. Of course, the possible values for x are 0, 1, 2, up to capital N, and so x is a discrete random variable. Now here we set n is equal to 10 and p is equal to 0.5. The possible x values in this case are from 0 up to capital N, as we've just said, and we let the y values be the PDF of the binomial distribution evaluated at these x values. And these look as follows. So the probability here of having 0 successes is this very small number, 0.000975, etc. The probability of having 5 successes is 0, 1, 2, 3, 4, 5 is this number here, i.e. about 0.25. If we plot the probabilities, this is what the probability mass function looks like. The only possibilities are 0, 1, 2, 3, 4, 5. They start at very small probabilities. The probability of having 5 successes is about 0.25, as we see. And then they decrease again. For any of the values of little x outside these integers 0 up to 10, the probability that capital X takes that value is 0, and this is not shown. So a probability mass function is typically shown discretely. We will now see how the probability mass function relates to the cumulative distribution function. The probability mass function is shown in dark blue over here. The cumulative distribution function is shown in light blue. And as you can see, at each of the points where the mass function has mass, in other words, at the integers from 0 up to 10, the cumulative distribution function has a jump. Moreover, the size of the jump is exactly the height of the mass function. So, for example, this length over here corresponds exactly to this length over here. Similarly, this length over here, this jump, corresponds exactly to this probability here. Let's now have a look at a similar situation for a continuous random variable. In this case, we look again at the standard normal distribution. We've already seen the normal CDF. Its derivative is the standard normal PDF, or the so-called bell curve. As you can see, the slope of the CDF, the rate curve here, is 0, and so the derivative of the rate curve is 0 here. The slope over here is 0 as well, and so the value of the PDF is 0 over here. The slope increases, reaches a maximum, and then the slope starts to decrease. And that means that its derivative increases, reaches a maximum, and then starts to decrease. Since the CDF is an increasing function, its slope is always positive, and this means that the probability density function is always positive. Note that if x is a continuous random variable and a is less than b, then the probability that x lies between a and b is the integral of the probability density function from A to B. And this is just the area under the graph of the density function between A and B. So for example, the probability that x lies between -1 and 2 is just this shaded area. In particular, the cumulative distribution function of capital X evaluated at little x is by definition the probability that capital X is less than or equal to little x. And that is this integral here, which is just the area from -infinity to x. So for example, the value of the CDF at this point here, in other words its height, is equal to the shaded area. Histograms are a method for obtaining an approximation of the PDF from data. Suppose, for example, that we have independent rules x1 up to xn from some common distribution f. We divide the range of these data points into bins, each bin being an interval of real numbers, and above each bin we plot a rectangle whose height is the proportion of observations in that bin divided by the width of that bin. Here the proportion of observations in the bin is simply the number of observations in the bin divided by the total number of observations, in other words, by the total number of data points. The sum of the areas of all the rectangles is then equal to 1, as is the area under a probability density function. To see this, suppose that the jth bin contains nj many data points, that its height is hj, and that its width is wj, for j is equal to 1 up to capital J. In other words, there are capital J many bins. The total number of data points is then equal to the sum of all the nj. It follows by definition that the height is the proportion of the data points in the jth bin divided by the width. This means that the area of the jth bin is just the product of the height with the width, which is just nj over n. Now here we have n many data points, and nj of them fall in the jth bin. So the probability that a data point lies in the jth bin is approximately equal to nj over n. In other words, the area of the jth rectangle is approximately equal to the probability that a data point lies in the bin. In that case, the sum of the areas of the rectangles is just the sum of the products hj, wj, which is just the sum of nj over n. And since the sum of the nj's is equal to n, the sum of nj over n is equal to 1. A histogram can therefore be regarded as an estimator of the common probability density function of the data points xi. Let's have a look at an example. We draw n is equal to 50 random numbers from the standard normal distribution, and we'll have a look at the resulting histogram. So first we draw 50 random numbers. Here they are. They're sort of all over the place, so it's not a bad idea to sort them so we have an idea of the structure. You can see they lie between -2.5 and 2.07. Now let's have a look at the resulting histogram. In this case, the bin widths are 0.5, starting at -3 and ending at 3. Let's have a look at the bin between -1.5 and -1. In other words, this bin over here. Its height is just over 0.1. If we look at the number of data points between -1.5 and -1, we have 1, 2, 3 data points. So the height of the third bin should be 3 over 50, that's the proportion of the data points in that bin, divided by the bin width, and that's 0.12. And we can see, in fact, this bin is about 0.12. In the same way, if we look at, say, the data points between 1 and 1.5, this bin over here, well, this is 1, 2, 3, 4, 5, 6, 7 data points. So its height should be 7 over 50 over 0.5, that's 0.28, and we can see that in fact, yes, that is about 0.28 because this height over here is 0.3. If we plot this again with the normal PDF, we see that the histogram approximates the probability density function of the normal distribution. This approximation will get better and better if we increase the number here. So if we increase this to say 1000 points, we don't need to see it anymore, and we draw the histogram in the PDF, we get a much better approximation.